Hello everyone, welcome to the Eriez Bearing Vibration Reduction Project. For this project, we are analyzing an eddy current separator used mainly for recycling applications to separate metals from nonmetals. It is highly dependent on rotor efficiency at a certain nominal speed. The rotor has two bearings, one on each side, used for rotational efficiency. Current operation of this machine causes vibrational issues, and our goal is to reduce those vibrations. Our problem statement is to select a bearing to reduce vibrations of rotor operation at 3000 RPMs.
To begin our analysis, we used the SKF SimPro Quick software, where we imported our shaft as well as the bearings and specified constraints on the non-drive side and the drive side bearings to determine the stiffnesses during operation. Our next analysis is the bearing life calculation, where we did hand calculations as well as used the SKF software to determine the life of the bearings to ensure that they were above 60,000 hours as specified from Eriez.
From there, an ANSYS analysis was set up using the stiffnesses generated from the SKF tool. A static structural, modal, and harmonic analysis were all able to be completed using these stiffnesses.
Once the ANSYS model was created, a 3D state space FE8 MATLAB code was created to validate the ANSYS results as well as efficiently calculate critical speeds and transmissibilities. The MATLAB code discretized the shaft into several elements to account for the stiffness of the shaft and calculate bending modes. As shown in the figure, each element has its own stiffness, coordinate systems on each end, and dimensions.
From there, the critical speeds from both the ANSYS and the MATLAB code were used in a comparison process to ensure that both models were accurate. The yellow highlighted column represents the original bearing, while the other columns represent our bearing candidates. As you can see in the first three modes, the error stays within 5%, which is very good because those are the primary modes of study, while modes 4, 5, and 6 do not go above 10%. Shown here are the results of the FEA harmonic analysis for each location of a bearing in both directions. Note that the matching force used to derive the displacement force is in the non-drive direction on the vertical side, which could cause numerical error on the other locations in terms of magnitude. However, the reduction will remain constant.
Transmissibilities from the code are shown in this figure. As can be seen in this plot, the 1215 bearing is the best candidate when compared to the other bearing cases.